last talk of the day, Bhargava's number 2.
Yeah. Okay. Can you hear me okay? Yeah. Okay, so what I want to do today is talk about n equals 4. So just to recap what we were doing last time, so I want to classify rings of rank n. Okay, where a ring of rank n means a ring whose additive group, underlying additive group, looks like z to the n. Okay, so we did n equals 1, 2, and 3 last time. So n equals 1, there's just one ring, it's just z. N equals 2, we saw that the quadratic rings of rank 2 are classified by their discriminants, and discriminants are always 0 or 1 mod 4. Okay, so quadratic rings are classified by those integers that are 0, 1 mod 4. There's a unique ring of that discriminant for any such number. Okay, then for n equals 3, we saw that rings are not anymore classified by their discriminants. They're classified by more information, namely integral binary cubic forms, up to GL2 equivalents. So maybe just to show you the picture of the n equals 3 slide. So the way n equals 3 was discovered was you wrote down its multiplication table, and you saw that these 4 coefficients a, b, c, d determined everything, and they transformed just like a binary cubic form. Okay, so that's how the n equals 3 case worked. And the n equals 3 case, so the binary cubic form, the question was, what is the meaning of that binary cubic form? And the reason I cared about the meaning is because I was interested in n equals 4. So n equals 4, as I was pointing out last time, cannot be solved in this way. You can't just write down a basis and look for some subset of coefficients that then determine everything using the associative law. That's what happened for n equals 3. It doesn't work for n equals 4. Because you can show that there are no subset of coefficients that are independent that can just that determine everything else. So n equals 4 has to be approached differently, and the way to try to approach it differently is first to re-understand n equals 3 from a different perspective. And so one first question was, well, this ABCD form the coefficients of a binary cubic form. What is the meaning of that binary cubic form? And the meaning of the binary cubic form, one meaning that I pointed out last time, is that this binary cubic form gives the most fundamental map from the cubic ring to its quadratic resolvent. So that's what we talked about last time. So given a cubic ring, there's a quadratic resolvent, namely the ring that has the quadratic ring that has the same discriminant as the cubic ring. What I didn't mention last time is that any ring of rank n, its discriminant, as I defined it last time, is always 0, 1 mod 4. Okay, that's the theorem of Stickelberger. So given any ring of rank n, it's going to have discriminant 0, 1 mod 4, and so there will be a unique quadratic ring that has that discriminant. Okay, and that's what we call the quadratic resolvent of a cubic ring. And given a cubic ring, you form its quadratic resolvent, there's a natural map that preserves discriminants to the quadratic ring. And so it's given by this, and that map descends to a map from R mod z to S mod z, where R is the cubic ring, S is the quadratic resolvent. So this natural map from a cubic ring to the quadratic ring actually descends mod z, so you get a map from R mod z to S mod z, it's a cubic map. And so that's the meaning of the binary cubic form. That's a binary cubic form. So this binary cubic form that corresponds to a cubic ring is the most fundamental map from a cubic ring to its quadratic resolvent that preserves discriminants. Okay, so that's one way of viewing this correspondence in the case n equals 3. Okay, so that's just a recap from last time. The reason I wanted to recap that is because we want to take that model and try to apply it to solve the n equals 4 case. Okay, so take this different perspective to try to solve the n equals 4 case. Okay, so these are all slides from last time. Okay, so this is how we started n equals 4. Okay, we're given a quartic ring, and we wanted to find a cubic ring of the same discriminant. Okay, just like we did in the cubic case, we find a quadratic ring of the same discriminant. So now we're going to start with a quartic ring. We want to find a cubic ring of the same discriminant and a map phi that preserves discriminants. Okay. And the map phi we found is as follows. So if you have an element x in a quartic ring, and x prime, x double prime, x triple prime are its conjugates. Okay, so this quartic ring we're assuming is an order in an S4 quartic field. Then I pointed out that this classical map, phi of x equals x prime plus x double prime, x triple prime. This thing has three conjugates. Okay, so it's taking a quartic element x and mapping it to something that has three conjugates. So it's mapping to something in a cubic field, something cubic. Right? And so I hope you all did this exercise, that it preserves discriminants. Okay? If you take the product of the pairwise differences of the conjugates of this has three conjugates. You get exactly the product of the pairwise differences of these four conjugates. Okay? So that's something very pretty. And it's something we can use to try to parametrize quartic rings. Okay, so what can we do with this? So actually we're going to proceed just like we did in the cubic case. So this is our fundamental map from a quartic ring to some cubic ring. Okay? You take an element in a quartic ring and it maps you to some cubic ring. And so this phi, again, has two properties. Just like in the cubic case. So phi has two properties, again. And they're exactly the same. I could have just used that slide from the cubic case again, but I'll write it again. So phi has two properties, namely, phi is discriminant preserving. Okay? Just like we had in the cubic case, going from the cubic ring to the quadratic resolvent. Here we have a map from a quartic ring to a cubic ring, and that map is discriminant preserving. In other words, discriminant of phi of x is the discriminant of x. And the other point is that phi, again, descends to a map modulo z. So it descends to a map phi bar from q mod z, to r mod z. So why is that? Okay, so I just want to keep phi up there. So why is that? Well, if you look at phi of x plus some constant c in z, what happens? Right? If you take phi of x plus a constant, right? So if you just put x plus a constant here, well, you're going to get phi of x again. But then you're going to get, right, if you have x plus c, then you're going to get cx prime, and you have x prime plus c, so you're going to get cx. So if you think about it, you're going to get phi of x plus c times trace of x, right? Because you're going to get a term cx, a cx prime, a cx double prime, a cx triple prime. Right, what are the conjugates of x plus c? That's x prime plus c, x double prime plus c, x triple prime plus c. So if you take phi of x plus c, you get phi of x again, but plus c times trace of x, and then you also get 2c squared, I think. Is that right? Yeah. Well, this thing is in z, right? C times trace of x plus 2c squared, this thing is in z. So when we translate x by something in z, the image also gets translated by something in z. So this phi descends to a map from q mod z to r mod z. Right? Again, just like in the cubic quadratic case. Okay, now q mod z as a z module, what is this isomorphic to? Well, q is a quartic ring, so q mod z looks like z3. Right? And r mod z, r is a cubic ring, so r mod z looks like z2, right, as a z module. Okay, and what is the degree of this map? Well, it's quadratic. Right? So we have a quadratic map from q mod z to r mod z. So it's very analogous to what So it's very analogous to what happened in the cubic case. We had this fundamental map phi down to a lower rank ring that was discriminant preserving, and it descended to a map mod z. And in the cubic case, we saw that this was z2 and z, and it was a cubic map, so we got a binary cubic form. So what are we getting here? here we have Z3 and Z2, and it's a quadratic map. So a quadratic map from Z3 to Z2, you can think of that so it's a quadratic map on Z3, so it's a ternary quadratic form, but since it's mapping to Z2, it's a pair of ternary quadratic forms, right? One for each coordinate, right? So you have a ternary quadratic form mapping to one coordinate of Z2 and one to the other coordinate of Z2. So phi bar can be viewed as a pair, say A, if we pick a basis for Z2, right? Then to the first coordinate you have a ternary quadratic form mapping from Z3 to that coordinate, and then another ternary quadratic form mapping from Z3 to the second coordinate. So you can view phi bar as a pair, A comma B, of ternary quadratic forms. Right, so these are integral, of course, integer coefficient, integral ternary quadratic forms. Right? So instead of binary cubic form, we're getting a pair of ternary quadratic forms in this case. And everything is so analogous with the cubic case that it seems to indicate that quartic rings, if everything goes analogously from here on, then quartic rings should correspond to pairs of ternary quadratic forms up to equivalence, right? So what does up to equivalence mean? Well, you can change the basis here by an element of GL3 that acts on the ternary quadratic forms, right? GL3 acts on ternary quadratic forms. And then Z2, you can change the basis here, and that'll change the base. So A and B span some two-dimensional space of ternary quadratic forms. GL2, when it acts on this basis, will just change the basis of that two-dimensional space of ternary quadratic forms. So this pair of ternary quadratic forms we get is well defined up to this GL3 cross GL2 equivalence. Okay. So if everything's analogous, we should expect that quartic rings should correspond to pairs of ternary quadratic forms, integral ternary quadratic forms, up to GL3 cross GL2 equivalence, okay, if everything goes analogously. Okay, so, well, to prove such a statement, we have to know, given a pair of ternary quadratic forms A and B, how can we recover Q and R, say? Okay, well, there's sort of one problem that I haven't mentioned, which is, what is this R? Okay, so, right, in the cubic case we said a quadratic resolvent is something that has the same discriminant. But remember, discriminants don't classify cubic rings. So if we just say R is a cubic ring having the same discriminant, that doesn't specify R. Right. Okay, so I think I should first talk about what is R. So there's still a lot of things to sort of sort through here. So what is R? So, okay, well, let me write the definition of a cubic resolvent ring and say what properties we'd like it to have. So a cubic resolvent ring of a quartic ring oops, quartic rings are always Q. A quartic ring Q, well, it's a cubic ring. It's a cubic ring R. And what properties do we want it to have such that, well, first of all, we want the discriminants to be the same, right? Just as in the cubic case. So such that discriminant of R equals discriminant of Q. And what other property do we want it to have? We want R to contain, remember we had this map. So we want R to contain the image of phi, right? Because phi is a map from Q to R. So we want R to contain phi of x, right? If we want this map phi to be a map from Q to R, then R better contain the image of phi, right? So we want discriminant of R to be discriminant of Q, but we also want R to contain phi of x for all x in Q. Right? So if we have such an R that contains the image of phi of x for all x and q, and its discriminants are the same, then we can talk about this map free from Q to R. Right? So that's what we mean by cubic resolvent ring. Now the problem with this definition, is that, first of all, it's not clear that such an R exists. And if it does exist, there may be many. Right? It's not clear that it's unique. And in fact, in general, it's not unique. So how do you pick out one that's somehow special over the others? And the answer is you can't. There's nothing special about any of them. If there are many of them, they're all equally good cubic resolvent rings. So you sort of want to treat them all the same, and so you call them all of them. You call all of them cubic resolvent rings, and it's sort of clear when you think about this that this cubic resolvent ring R will come along for the ride when we're talking about parametrization of quartic rings. Okay, so, but in any case, so once you're given Q, and so a quartic ring Q and a cubic resolvent ring R, that's it, with these properties, then you get a map phi bar from Q mod Z to R mod Z. This is the quadratic map, which gives rise to this pair AB of integral ternary. So pair AB of integral ternary quadratic forms. Okay, so you have to choose a cubic resolvent ring, which may or may not exist, as far as we can tell now. But it turns out it does always exist, which I'll tell you about in a little bit. So once you pick such a cubic resolvent ring R, then you get this pair AB of integral ternary quadratic forms by taking this map phi bar from Q mod Z to R mod Z. And that map exists because R, by definition, contains the image of phi. Okay, so if everything's going to be analogous with the cubic case, we now want to show. Okay, so now the question is, suppose we're given AB. Okay, so we're hoping that AB is going to sort of parametrize. These pairs of integer ternary quadratic forms are going to parametrize quartic rings. So first of all, the question is, if you're given such a pair of ternary quadratic forms, here's the first question: how to recover Q? Can you recover Q? Okay, is Q determined from that pair? So given a Q and an R, you get a pair of ternary quadratic forms. Conversely, given a pair of ternary quadratic forms, does it uniquely determine Q? That's the question. Right. Maybe I'll even say how to recover QR. I mean, does it actually determine both guys? Okay, so this is to go backwards. Okay, so given AB, can you recover Q and R? And the answer is contained in the following lemma. So this lemma is something that sort of contains a very beautiful property of this map phi bar. Remember, phi bar is the map x prime plus x double prime x triple prime, right? So what is this property of phi? So here's a remarkable property. So maybe I should just write what I'm supposing. So given Q and cubic resolvent R, and any elements x, y in Q, we have the following identity, which says that if you take the index inside Q, okay, of the lattice spanned by 1, x, y, and x times y. Okay. So what does this mean? This means Q is a quartic ring, right? It has rank 4. You can take the lattice, if you have two elements x and y, you can take the lattice spanned by 1, by x, y, and x times y. Okay? And you look at the index of that lattice inside Q. That's what I mean by that. It turns out that index is the same as the index inside R of the lattice spanned by, so R is a cubic ring, remember, of the lattice spanned by 1 phi of x and phi of y. So that's a very nice property of the map phi. So notice on the right there's no multiplication inside R, okay? And on the left there's just one multiplication inside Q. Okay? And so this is an identity. Okay, so what's the proof? Okay, well, what does this mean? Remember the discriminant of, so to prove this, you just observe that discriminant of Q is discriminant of R. And since those discriminants are the same, it suffices to check that the discriminant of this lattice is the same as the discriminant of this lattice. Right? And from algebraic number theory, if you remember how one computes discriminants, there's a determinant definition, right? It suffices to check. So since these discriminants are the same, it suffices to check the discriminants of these lattices are the same. So it suffices to check the following identity, right? So we write down the conjugates of 1, conjugates of x, conjugates of y, and conjugates of xy. Suffices to check that this what is phi of x, right? It's x prime plus x double prime, x triple prime. Should look more room. Okay, what's the other conjugate? X double prime plus x prime, x triple prime. And then the last conjugate is x triple prime plus x prime, x double prime. And the same thing for y. Y prime. Right, the same thing. So I took the conjugates of x, y, and xy, made that determinant, and took the conjugates of phi of x and phi of y and 1, made that determinant. Right, and that's just, this identity just says that the discriminant of that lattice is the discriminant of that lattice. Okay, so how do you check this? Well, you multiply it out. And it's true.
This is for generic.
Yeah, so this is just an identity in x and y. Yeah. Uh-huh.
It's not going to be, it may not span a full lap.
Right, that's right. Then this determinant will be 0, and this will be 0 too. So this is really an identity, regardless of what your x and y are. This is just an algebraic identity. Okay, so that's just true. Okay, so that's just a algebraic identity. Okay, so this is great. Okay, so I'll hide the proof now. Okay, so the proof is just a calculation, but it's a very beautiful identity involving this. And so how does this determine Q? Well, the point is that if A, B are fixed, right? So if you have some fixed AB, right, then AB, I mean, this pair of ternary quadratic forms, this is exactly, I mean, this is the map phi, right? So if AB is fixed, that means you know phi, right? And if you know phi, then you understand this side, and therefore you understand this side, and therefore you understand multiplication in Q. I mean, that's sort of the point. That if your AB are fixed, that means you understand this side, and if you understand this side, you understand this side because they're equal, but this side involves multiplication. And so that sort of fixes the multiplication law on Q. So let me just explain how that works. So if AB are fixed, then can use lemma to understand multiplicative structure of Q. As follows. So if you write, say you use a basis, so say you take Q, let it have basis 1, alpha 2, alpha 3. Okay. So 1 can write as alpha 0. Then the multiplication table of Q will look something like, well, alpha I times alpha j is going to be some Cij k, alpha k, right? And we need to determine these Cij k, right? Those are the structure coefficients of the multiplication table for Q. So how can one determine that? Well, we will let x and y be general elements of Q, right? So let x, say, equal, let it be Ri alpha I, okay, the general element of Q. And y be some other general element of Q, say some Si alpha I. Okay, so these are general elements of Q. Then xy will be some Ti alpha I. right, where Ti, but the Ti can be computed using theCijk, right? SoCijk are the multiplicative coefficients of Q that we want to figure out, and these Ti will depend onCijk and the Ri and the Si, right? So where Ti are polynomials in Ri, Si, andCijk. Right. Okay, but on the other hand, so what does the lemma? What does the lemma say? The lemma implies implies that if you take the lattice spanned by 1 xy inside Q, that index is just a determinant, right? The determinant is going to be R, right? R1, R2, R3, S1, S2, S3, and T1, T2, T3. That's equal to what's going on over here. So that's going to be this determinant, 1, and then you have your, right, your phi is your phi is this quadratic map from Q mod Z to R mod Z, which is just this AB, these ternary quadratic forms. So let me write it out and then I'll explain a little more. Oops, sorry. The R1, R2, R3, and B should have been S. Oh wait, what did I do? No, that was right. Sorry. And here's A of S1, S2, S3. Right, remember phi is just the map. I mean, phi is represented in terms of basis by AB. So 1 phi of x, phi of y is just that index is going to be this determinant, 1, and then the value of B on R1, R2, R3, the value of A on R1, R2, R3, and the value of B on S1, S2, S3, and the value of A on S1, S2, S3. Okay? So this identity tells you that you have this identity. So, but this is some polynomial in Ri and Si, and this is some polynomial. So let's call this P of R1 dot 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 S3, right? And this is some polynomial say Q of R1 dot 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 S3, right? And those 6 variables, R1, R2, R3, S1, S2, S3. And the point is that you have this identity all the time. So these two polynomials take the same values for all integers R1, R2, R3, S1, S2, S3. And so by equating coefficients, equating like terms, so equating coefficients of like terms, you get a bunch of equations in theCijk. Right? So a bunch of linear and quadratic equations in theCijk. And this system of equations in theCijk has a unique solution. So it's sort of a miracle. So assuming commutativity and associativity, so those also give you conditions on theCijk, you get a unique solution. Up to change of basis of the alpha I. So the point is that if you fix the map phi, in other words, you fix the pair of ternary quadratic forms A and B, that actually determines the multiplicative structure of Q entirely. So what that means is that structure of Q is determined because of that miraculous identity involving phi. So if you fix AB, because AB is representing that map phi that has that amazing identity property, AB actually completely determines the structure of Q. Similarly, structure of R can be determined. So remember, we haven't determined the structure of R yet, because that identity only involved multiplication in Q, but not in R. Okay, so we need another identity that tells you, that'll sort of tell us what the structure of R is, and here's the identity. It looks very similar. So here's the next lemma. Index in Q of, so let's say x is in Q. An index of Q of 1, x squared, x cubed is the same as the index in R of 1, phi of x squared, out here. Okay, so to determine this, you need to know the multiplication in R. Do you recognize this identity? This identity is just saying that the map phi is discriminant preserving. Okay. So if you think about it, that's all it's saying, right? This is saying the index of z bracket x inside Q. This is saying the index of z bracket Q of x inside R. And the fact that those are always the same is just equivalent to saying that phi preserves discriminants of elements. Because what is the discriminant of x? It's just the index. What's the discriminant of x? Is just the discriminant of z bracket x. Right? What's the discriminant of phi of x? Just the discriminant of z bracket phi of x. Okay, so this is an identity, and one proceeds the same way. So now we already know the multiplication structure on Q, so we can understand this side. And we don't know the multiplication structure on R yet, but since we have this identity, using the same argument that we just had, where we just put in indeterminates for x, right, as a general linear combination of a basis for Q, and you write down a basis for R, you write down phi of x in terms of that basis, in terms of A and B, right? A and B represents the map phi. You just use indeterminates, and you determine the multiplication structure on R. It's uniquely determined. So same arguments determine multiplication structure on R. Now, remember, what classifies cubic rings? Binary cubic forms. So if we're determining a multiplication structure on R, that means we're determining some binary cubic form in terms of A, comma B. So what is that? That binary cubic form corresponding to R, it turns out it's a very natural thing. It's just the determinant, well, it's actually 4 times the determinant of, remember A is a ternary quadratic form, so you can talk about its determinant, right? You can take that A and multiply by an indeterminate x, and then you can take the other ternary quadratic form B, multiplied by an indeterminate y, okay, and you subtract them, and you take the determinant, right? And the determinant of a ternary quadratic form is a degree 3 map, right? So this is a binary cubic form. And that exactly is the binary cubic form corresponding to that cubic ring R. So this identity allows you to show that it determines the cubic ring R, and if you check what that binary cubic form is, it's exactly the natural binary cubic form that you can get from a pair of ternary quadratic forms. Namely, you take the determinant of AX minus BY. So that's as nice as it can be. And so that is essentially proves that it's a bijection. So given a pair Q comma R, where R is a cubic resolvent of a quartic ring Q, you get a pair of ternary quadratic forms A comma B, and given A comma B, you can actually recover Q and R back. Okay. Now, of course, in all these arguments, we were assuming that everything is in order in an S4 field. So maybe I just wanted to say for a few minutes what we would mean if you're not in order in an S4 field. How could you define a cubic resolvent? Well, it could be any quartic ring. So I want to define a cubic resolvent in general. So let Q be a quartic ring. So then a cubic resolvent is going to be a triple. It's going to consist of a cubic ring It's going to consist of a map phi bar from Q mod Z to R mod Z, and it's going to consist of this isomorphism delta, which I'll tell you in a sec what that is. So this is called a cubic resolvent. It's a cubic resolvent of Q if the following properties hold. So first of all, phi bar, okay, that we've already seen before. This is a map from Q mod Z to R mod Z. Okay. And this should be quadratic. Okay, so we already saw this in the case of orders. We had a map phi bar that was given explicitly by xx prime plus x double prime x triple prime. For a general quartic ring, we're just going to require this phi bar to come along with R as this quadratic map. Okay, the second property is that this delta, okay, this was already hidden in what I was saying, but we didn't need to make it explicit in the case of orders. The delta is a map from wedge 4, this top wedge power of Q, to the top wedge power of R. Now what this means is that we're sort of assigning simultaneous orientations to both Q and R. So Q is oriented in a parallel way to R. And this was sort of coming up, I sort of didn't say this before, but this determinant identity is true. Well, actually, I'm not sure it's true. It might be plus or minus over here. Okay, it's going to be true assuming you order the conjugates correctly. Right? So you're going to get plus if you order the conjugates correctly. And that's equivalent to saying that you sort of fix some compatible orientations on Q and R. So that's... Yeah, isomorphism, yeah. So this is an isomorphism. Right, thanks. Right, so delta gives a compatible orientations on Q and R, and that allows that identity that we want to be true, okay, with the plus sign. Okay, and the other property we want is that, okay, so we have this map from wedge 4Q to wedge 3R, and then we want this delta to take one wedge X, wedge Y, wedge XY. Okay, so we want that. We want the analog of that identity that we had, that great identity, right? So delta of one wedge X, wedge Y, wedge XY. We want that to equal. Okay, so that's going to map you into wedge 3R, and what do we want to get in wedge 3R? We want to get one wedge. Okay, so I didn't do this very well, but okay. So phi is any lift of phi bar from Q to R. Okay. So we want this phi and delta to be related in this way. Right. And this was, remember, these are all things that were true for that map that we had xx prime plus x double prime x triple prime. We're just isolating the properties that one needs in general. And the last property is that R, under the Stillone-Faddeev-Gann-Gross correspondence, actually corresponds to, so if you write, so this is quadratic, so that means phi bar can be represented as like an AB, pair of ternary quadratic forms, and we want R to actually be given by 4 times the determinant of AX minus BY. Okay, so these are all the properties that we had in order to determine from AB the structure on Q and R, and so we're just isolating those properties. So for a general quartic ring, if we talk about a cubic resolvent, we're talking about a cubic ring that has all those properties that we had when we were taking that xx prime plus x double prime x triple prime map. And what properties were those? We had a map from Q mod Z to R mod Z that's quadratic. We had compatible orientations. The index of 1 x, y, xy inside Q was the index of 1 phi of x, phi of y inside R. And then we had that the multiplicative structure on R is just given by that natural binary cubic form that comes from a pair of ternary quadratic forms. Right. So from this pair of ternary quadratic forms, there's a natural way to construct a binary cubic form, namely you take determinant of AX minus BY, and we want R to actually be given by that binary cubic form under the Dillon-Faddeev correspondence. Okay. So that's a way of defining, and I didn't talk about this in the cubic case, but again, in the cubic case, one could have done something similar. You isolate the properties that you need, and you don't have to restrict yourself to orders. You can talk about general cubic rings, general quartic rings. And actually, with these definitions, you don't even have to just work over Z. You can talk about cubic rings over an arbitrary base. And if you take a definition of cubic resolvent in this way over an arbitrary base ring, then you can carry out a lot of these theorems over an arbitrary base. Okay, so that's what we mean by a cubic resolvent in general. And once we have that definition of a cubic resolvent, then we have the main theorem, which is now theorem 4, since we're in the case n equals 4. So this is a theorem for my thesis. So the theorem is how to classify rings of rank 4. It's as follows. So it says that pairs QR, where Q is a quartic ring, and R is a cubic resolvent, so sets pairs up to isomorphism. Okay. So pairs. So it's a little bit different from the theorems 1 through 3 in that this cubic resolvent is now sort of coming along for the ride. These things are in one-to-one correspondence, but it's actually not different because the quadratic resolvent was coming along for the ride. We just didn't notice because it was unique. So okay, you didn't really need to write it down. So these things are in one-to-one correspondence with pairs of ternary quadratic forms, pairs A, B of integral ternary quadratic forms modulo GL2 cross GL3 C equivalence. Okay, but the statement is very similar as in the cubic case. You have, before we had a cubic ring and its quadratic resolvent, those things up to isomorphism were in one-to-one correspondence with binary cubic forms up to GL2Z equivalence. So it's just been replaced by a quartic ring and a cubic resolvent, and binary cubic forms have been replaced by pairs of ternary quadratic forms. And the group is now, that's naturally acts as GL2 cross GL3Z. Okay, so that's the theorem. So it's very, very analogous to the cubic case from this point of view. The only difference is that there's this R hanging around. Okay, and we want to get a handle on what that R is. So first of all, does this cubic resolvent ring always exist? That's a first question. And second is, if it exists, how many are there? Right? So now that we had algebraic definitions for the definition of resolvent ring, but now that we have this correspondence, we can actually study, you fix your quartic ring, and you can actually study how many cubic resolvent rings are by looking at this side now, by doing invariant theory of this representation. So one can now, once the correspondence is there, you can use whichever side is more convenient for the question that you're asking. So actually can do invariant theory on this side. So for example, you fix your quartic ring, you fix all the multiplication coefficients on Q, and then you look at the possible pairs that can arise on this side. And the number of pairs that arise on this side is the number of cubic resolvent rings. So that's just some invariant theory work that one can do. And what one finds is that, well, you can actually determine exactly the number of cubic resolvent rings of a given quartic ring. So I'll just tell you. So the number of cubic resolvents, and there's an analogous computation you can do in the binary cubic case. You can find the number of quadratic resolvents in the same kind of way, invariant theory, where you always get one. Okay, but that's something we knew already, but you can. I had to do that first just to understand that you could use this side. Okay, so the number of cubic resolvents of a quartic ring is equal to the number of index. So let's call this quartic ring Q. Is equal to the number of index content of Q. I'll tell you what content of Q means in a second. It's the number of index content of Q sublattices of Z2. So the number of cubic resolvents is just the number of index n sublattices of Z2, where this n is defined as the sup of all k such that there exists some Q prime quartic ring such that Q equals Z plus K Q prime. So given any quartic ring Q prime, you can always sort of multiply it by K, right? By taking all the structure coefficients and multiplying them by K. And that's this ring. So Z plus KQ prime is a ring for any Q prime and any K. And if Q is sort of this multiple of K, then you say the content of Q is a multiple of K. And if you take the biggest K for which Q is a multiple of K, that's called the content of Q. Okay. So the content is always at least 1. But sometimes it can be bigger. And what we're saying is that the number of cubic resolvents of a quartic ring is the number of index n, where n is an integer at least 1, sublattices of Z2. So in particular, it's always at least 1. Right? So a corollary is that every quartic ring, okay, and this was something that was not obvious at all from the algebraic definition. Right? From the algebraic definition of a cubic resolvent, it wasn't clear that any cubic resolvents existed. But then once this correspondence is there, the invariant theory of this side tells you this theorem, and so we find that every quartic ring has a cubic resolvent. Something that was obvious in the quadratic case, it's not as obvious in the cubic case. In the cubic case, it was obvious that there was a quadratic resolvent. In the quartic case, it's not obvious that you always have a cubic resolvent. But once this theorem is established, then you can do invariant theory to show that you always have a cubic resolvent. And if your content is 1, for example, if you're the ring of integers in a number field, your content is 1. And so a number of index 1 sublattices of Z2 is just 1. And so for maximal orders, in other words, for rings of integers in a number field, there's a unique cubic resolvent. That's what this shows. Something that's not obvious just by thinking about it algebraically, but this invariant theory shows that every ring of integers, every maximal order has a unique cubic resolvent. So that's great. So that tells you that in this theorem, every single quartic ring arises in this bijection, and it tells you that rings of integers is actually a bijection on rings of integers. Okay, and that's the rings. So this gives a fairly good theory for n equals 4. It allows you to do essentially all the things that were useful in the case n equals 3 using binary cubic forms. One can now do for n equals 4 using pairs of ternary quadratic forms. Any questions about this correspondence? So it should look fairly analogous to the binary cubic case if I presented it okay. No. That's a good question. Right. So for orders and number fields, the content is always finite. But if you take some very degenerate rings, then the content can be infinity. And this statement is still true in the case where the content is infinity. So you have infinitely many cubic resolvents sometimes when your ring is very degenerate. Yeah, good question. Okay, so I'll just end by... Okay, so that was the case n equals 4. So next time I'm going to do n equals 5, but I want you to think about a couple of things. First of all, so all these things, there's a sort of unified picture of all these cases. There's sort of a geometric picture. So if you take a binary cubic form, right, and you take its roots, right, you can talk about the roots of a binary cubic form. The roots of a binary cubic form lie in P1, right? Right, so it's the set of all x comma y, such that if you insert it into your binary cubic form F, you get 0. Okay, and those are naturally defined as elements of P1, right? Pairs x comma y up to scaling. So a binary cubic form has 3 roots in P1. So if you have your P1, you get 3 points. Right, a binary cubic form sort of cuts out 3 points in P1. And they're not going to be defined over the integers. They'll be conjugate to each other. So they'll be defined over some cubic field, say, or maybe 1 will be rational and 2 will be defined over a quadratic field. But that cubic field that you get, so you take your binary cubic form and it cuts out a cubic field, say these points are defined in a cubic field, these roots, then that order that we were associating to the binary cubic form is actually sitting inside this cubic field, where the root is defined. So similarly, if you take a pair of ternary quadratic forms, you can talk about, so what is a ternary quadratic form? It's a conic in P2, right? Ternary quadratic form corresponds to a conic in P2. So if you have 2 conics in P2, right? If you have 2 conics in P2, right? So here we're in P2. by Bayes' theorem, they intersect in 4 points. And so those 4 points will be defined generically over a quartic field. And that order that we were associating to that pair of ternary quadratic forms is actually an order inside the corresponding quartic field that these points will be defined over. Yeah. Okay, so what is the correct object here to get 5 points? Right, that's sort of a geometric question. So, and this will probably be P3 then. Right. So we're sort of looking for that object whose roots are going to give you. So that's a geometric way of trying to generalize this picture further to go up to n equals 5. So that's a geometric thing. So I'm just trying to motivate how one might go about thinking about n equals 5. And these are all things that I went through for years when I was thinking about trying to parameterize n equals 5. And one last thing. So that's a geometric thing that leads up to n equals 5. Then there's sort of a combinatorial picture. If you have 3 points, say you have 3 points, and you want to go to 2 points, how do you do that? Well, okay, if you have 3 points, there's sort of 2 things that you can do to 3 points. You can orient it this way, right? Or you could have oriented the other way, right? Or, right, you could have gone the other way. So there's sort of 2 orientations. And that's your map from 3 points to 2 points, because there's from 3 points you can go to 2 points by taking the 2 possible orientations. And that sort of corresponds to that fundamental map we were talking about from a cubic ring to its quadratic ring. So now suppose we take 4 points. What's the natural way to go to 3 points? Well, what are things that you can do to 4 points in 3 different ways? You can divide up the 4 points, yeah, right, exactly, into pairs of points. So there, you can do this, or you can do, right, you can divide it this way, right? Or you can take these, right? These here and then these, right? So right, you can group these 2 together. You can group these 2 together, or you can group these 2 together. Right? Okay. So there are 3 ways of dividing up 4 points into pairs of 2 points, right? And that's your map from 4 points to 3 points. So that's sort of your resolvent map. So to go to n equals 5, what turns out, you need to take 5 points and map it to 6 points. It goes up. There's actually no natural map from 5 points to a lower number of points. That's something that's something I want you to think about. So there's a natural way from going to 3 to 2. There's a natural way to go from 4 to 3. There's no natural way to go from 5 to something lower. That has to do with the fact that the quintic is unsolvable. But you can go from 5 to 6. And so for next time, I wanted you to think about these 2 things. Geometrically, how can you think about 5 points in P3? And also, combinatorially, how can you go from 5 points to 6 points? Both of these things are sort of key in understanding case n equals 5. So that's next time. Okay, thanks.